Have you ever looked up at the night sky and felt something stir inside you? That primal pull toward the unknown, the sense that we're meant for something more than this one pale blue dot. Tonight, we're going to explore one of the most profound questions humanity has ever asked. Will we ever truly break free from our cosmic neighborhood and venture into the vast ocean of stars beyond? Before we dive in, I'd be incredibly grateful if you consider subscribing and giving this video a thumbs up. Also, I'm curious, where are you watching from tonight? Drop your location in the comments. There's something beautiful about people scattered across our planet, all contemplating the same cosmic mysteries. Let's begin. Right now, as you're listening to these words, there are 5 spacecraft racing away from our sun at speeds that would make any terrestrial vehicle look like it's standing still. Voyager 1 and Voyager 2, launched back in 1977, have already crossed into interstellar space. They're out there right now, floating through the void between stars, sending back whispers of data about a realm no human has ever directly experienced. These missions weren't designed to leave our solar system. They were built to study Jupiter and Saturn, maybe catch a glimpse of Uranus and Neptune. But something remarkable happened. After completing their primary missions, they just kept going. They had enough velocity from their planetary encounters to break free from the sun's gravitational embrace, and now they're humanity's first ambassadors to the galaxy. Here's what makes this both thrilling and humbling. 8,000 miles per hour, these at their current speeds, traveling at roughly 30 spacecraft, would take over 70,000 TPO. 70,000 years. 2 years to reach the nearest star system. That's not to put that in perspective. 70,000 years ago, modern humans were just beginning to migrate out of Africa. We hadn't invented writing, agriculture, or the wheel. Entire civilizations would rise and fall before these probes reached another star. This is the brutal reality we're facing when we talk about leaving our solar system. The distances involved aren't just large, they're so incomprehensibly vast that they challenge every instinct we have about travel and journey. Think about the farthest you've ever traveled. Maybe you've flown across an ocean, perhaps you've driven cross-country. Those journeys feel significant because they take hours or days. But interstellar space operates on scales that make those trips look like stepping across your living room. Our nearest stellar neighbor, Proxima Centauri, sits about 4.2 light-years away. That means if you could somehow travel at the speed of light itself, racing through space at 186,000 miles per second, it would still take you over 4 years to get there. The speed of light isn't just fast, it's the ultimate speed limit of the universe according to everything we know about physics. Nothing with mass can reach it, let alone exceed it. This isn't just an engineering challenge we might overcome with better technology. This is a fundamental law written into the fabric of reality itself. So when we ask whether we'll ever leave our solar system, we're not asking if we can build a better rocket or develop more efficient fuel. We're asking whether we can somehow transcend the basic laws that govern how the universe works. We're asking whether human ingenuity can find loopholes in physics itself. But here's where the story gets interesting. Throughout history, humans have consistently achieved things that previous generations considered impossible. We've split atoms, landed on the moon, and mapped the human genome. We've built machines that can think, communicate instantaneously across the planet, and peer billions of years into the past. Every single one of these achievements required us to push beyond what seemed possible at the time. The question of interstellar travel sits at the intersection of physics, engineering, biology, and philosophy. It forces us to confront not just technical limitations, but fundamental questions about what it means to be human. If a journey to another star takes longer than a human lifetime, who makes that trip? If consciousness can be digitized and transmitted, does the physical journey even matter? If we genetically engineer humans to survive centuries in space, are they still human in the way we understand the term? These aren't abstract philosophical puzzles. They're practical problems that anyone seriously planning interstellar missions would need to solve. And the fascinating thing is that people are seriously planning these missions right now. Let me tell you about Breakthrough Starshot. This is a real project, funded with real money, designed to send actual probes to another star system within our lifetimes. The concept is elegant in its simplicity. Instead of carrying fuel for propulsion, you leave the engine behind on Earth. You build tiny spacecraft, no bigger than computer chips, and attach them to ultra-thin reflective sails. Then you point an enormous array of ground-based lasers at these sails and blast them with concentrated light. The pressure from the laser light pushes against the sails, accelerating these miniature probes to about 20% the speed of light. At that velocity, they could reach Proxima Centauri in roughly 20 years. 20 years instead of 70,000. That's the difference between impossible and merely incredibly difficult. The project faces enormous technical challenges. The laser array would need to generate power comparable to a nuclear reactor, focused with precision that exceeds anything we've ever achieved. The tiny spacecraft would need to survive acceleration forces millions of times stronger than Earth's gravity. They'd need to operate flawlessly for 2 decades in the radiation-soaked environment of interstellar space. And then they'd need to transmit their findings back to Earth across 4 light years, using transmitters no larger than microchips. But here's what's revolutionary about Breakthrough Starshot. It's the first serious, funded attempt to develop technology specifically designed for interstellar travel. It brings together leading experts in photonics, material science, and spacecraft design, all focused on solving problems that stand between us and the stars. It represents a fundamental shift from dreaming about interstellar exploration to actually engineering it. The project illustrates something crucial about how we're approaching the interstellar challenge. We're not waiting for some magical breakthrough that solves every problem at once. We're taking incremental steps, solving problems one at a time, building capability systematically. Each success enables the next, more ambitious goal. This approach is already bearing fruit in ways most people don't realize. The private space industry has reduced launch costs by over 90% in just the past 2 decades. Companies like SpaceX are making space access routine in ways that seemed impossible when they started. Blue Origin, Rocket Lab, and dozens of other companies are pushing boundaries and proving that space exploration doesn't have to be the exclusive domain of government agencies with unlimited budgets. This democratization of space technology creates opportunities that simply didn't exist before. When launch costs drop from tens of thousands of dollars per kilogram to hundreds of dollars per kilogram, entirely new categories of missions become feasible. We can afford to be more experimental, more ambitious, more willing to take risks on technologies that might fail. And that's exactly what we need for for interstellar exploration. Because the truth is, we're not going to solve this problem with one brilliant breakthrough. We're going to solve it the same way we've solved every other impossible challenge in human history. One small step at a time, building on each success, learning from each failure, gradually pushing the boundaries of what's possible until the impossible becomes inevitable. Consider what's happening with propulsion technology right now. Ion drives, once purely theoretical, are now routinely used for deep space missions. These engines accelerate spacecraft using electrically charged particles instead of chemical combustion. They're far less powerful than traditional rockets, but they can run continuously for years, eventually achieving velocities that chemical rockets could never reach. Solar sails have been successfully tested in space. These gossamer sheets of reflective material catch the pressure of sunlight itself, providing propulsion without any fuel at all. The acceleration is tiny, but it's constant, and over time it can build to significant velocities. Fusion research is making genuine progress, with multiple private companies claiming they're on the verge of breakthrough. If we can master fusion power, we could build rockets that convert hydrogen into helium, releasing enormous amounts of energy in the process. Such engines could theoretically accelerate spacecraft to 10% of light speed, making interstellar journeys feasible within human lifetimes. Each of these technologies represents a piece of the puzzle. None of them alone solves the interstellar travel problem, but together they're creating a foundation of capability that didn't exist a generation ago. We're building the infrastructure for interstellar exploration without fully realizing it. The same technologies that will make us a true spacefaring civilization within our own solar system are laying the groundwork for eventually venturing beyond it. The space economy emerging around Earth orbit, lunar exploration, and Mars colonization is creating the industrial base that could eventually support interstellar missions. But perhaps most importantly, we're developing something that might be even more crucial than any specific technology. We're developing the cultural and social frameworks for thinking in truly long-term scales. The companies and organizations working on Mars colonization are already grappling with projects that span decades. They're learning how to maintain institutional continuity across leadership changes, how to fund projects with uncertain timelines, how to motivate people to work toward goals they might not live to see completed. These are exactly the skills we'll need for interstellar exploration. Because regardless of what technology we eventually use to reach other stars, the projects will require unprecedented levels of long-term thinking and commitment. They'll need to survive economic downturns, political changes, and the natural human tendency to lose interest in projects that don't show immediate results. The space industry is already proving that such long-term commitment is possible. Companies like SpaceX have been working toward Mars colonization for over 2 decades, maintaining focus and momentum even when the goal seemed impossibly distant. The James Webb Space Telescope took nearly 30 years from initial concept to successful deployment, surviving multiple cancellations, budget crises, and technical setbacks. These examples suggest that we might be developing the institutional resilience needed for interstellar projects. We're learning how to build organizations that can sustain ambitious goals across multiple decades, how to maintain technical expertise across generations of engineers and scientists, how to adapt and evolve projects without losing sight of their ultimate objectives. But there's another factor that might be even more important than technology or institutional capability. we're discovering compelling reasons why we might need to leave our solar system. Not just because we want to explore, but because we might not have a choice. Astronomical surveys are revealing that our galaxy is a more dangerous place than we once thought. Gamma-ray bursts from distant stars could sterilize entire regions of space. Supernovae in our cosmic neighborhood could strip away Earth's ozone layer. Our own sun will eventually expand into a red giant, making Earth uninhabitable. Even more troubling, we're realizing that asteroid impacts, climate change, or other catastrophic events could threaten human civilization long before any of these cosmic disasters occur. From this perspective, interstellar travel isn't just an interesting scientific challenge. It's an insurance policy for the survival of human civilization. If we remain confined to one star system, we remain vulnerable to any number of events that could end our species. But if we can establish self-sustaining colonies around other stars, we create redundancy that could ensure human survival, even if Earth becomes uninhabitable. This existential motivation is already changing how people think about space exploration. Organizations studying long-term risks and the future of humanity are seriously examining the role that space colonization might play in mitigating them. Billionaires explicitly cite the need to make humanity a multiplanetary species as motivation for their space ventures. The combination of technological capability, economic opportunity, and existential necessity is creating conditions that favor interstellar exploration. We're developing the tools, building the institutions, and discovering the reasons why we might need to use them. But perhaps the most fascinating aspect of this emerging capability is how it's changing our understanding of what interstellar exploration might actually look like. We're moving away from visions of massive starships carrying thousands of people toward more realistic scenarios involving smaller, more focused missions that build capability over time. The first true interstellar missions will likely be robotic probes similar to Breakthrough Starshot, but more capable and sophisticated. These missions will teach us about the interstellar environment, test technologies for communication across interstellar distances, and possibly even begin preparing other star systems for eventual human presence. Following these initial probes, we might see waves of increasingly sophisticated missions, automated manufacturing systems that could begin building infrastructure around other stars, biological samples that could begin the process of terraforming potentially habitable worlds. Eventually, perhaps human crews or uploaded human consciousnesses that could establish permanent settlements. This step-by-step approach makes interstellar exploration seem less like an impossible dream and more like a natural extension of what we're already doing. We're not trying to solve every problem at once. We're building capability systematically, learning from each mission, using each success to enable the next more ambitious goal. And here's what makes this approach so compelling. We don't need to wait for revolutionary breakthroughs to get started. The technologies we need for the first steps already exist or are in development. We could launch interstellar precursor missions within the next few decades using extensions of current technology. Ion drives, solar sails, and nuclear power sources could carry sophisticated probes to the edge of our solar system and beyond, testing technologies and gathering data that will inform future missions. Each of these missions would teach us something new about the challenges of interstellar travel. They would test our ability to communicate across vast distances, to build systems that operate reliably for decades, to navigate in the space between stars. Most importantly, They would maintain momentum and interest in interstellar exploration, keeping the goal alive in public consciousness while we develop the more advanced technologies needed for human missions. The timeline for all of this remains uncertain. Robotic interstellar missions might be possible within 50 years. Human missions might require a century or more. But what's becoming clear is that the question isn't whether we'll ever leave our solar system. The question is how long it will take and what form that expansion will ultimately take. We're already taking the first steps, even if we don't always recognize them as such. Every advance in space technology, every successful long-duration mission, every new discovery about the nature of our universe is bringing us closer to the day when humans will look up at the night sky from the surface of a world orbiting another star. The journey has already begun. We just don't know yet where it will ultimately take us or what will become along the way. The transformation we're witnessing in our understanding of interstellar travel goes beyond just technological advancement. It's fundamentally changing how we think about time, distance, and what it means to be human. As we stand on the threshold of potentially becoming an interstellar species, we're discovering that the journey itself might be more important than the destination. Consider what happens when we start thinking seriously about missions that could last centuries. We're not just planning space missions anymore. We're designing civilizations. A generation ship traveling to Proxima Centauri wouldn't just be a spacecraft. It would be a complete society with its own culture, economy, government, and social structures that would need to evolve and adapt over the course of the journey. This raises questions that no human society has ever had to confront. How do you maintain cultural continuity across multiple generations of space travel? What happens when the people who arrive at the destination have never seen Earth, have no direct connection to the world their great-grandparents left behind? Are they still human in the same sense we understand the term today? The psychological research being conducted on long-duration space missions is already revealing how profoundly space travel changes human consciousness. Astronauts who spend months aboard the International Space Station report fundamental shifts in how they perceive Earth, humanity, and their place in the universe. They describe something called the overview effect, where seeing Earth from space creates a cognitive shift toward greater environmental awareness and a sense of unity with all life on the planet. Now imagine that psychological transformation extended over decades or centuries. The humans who eventually settle around other stars will likely have perspectives and priorities that we can barely comprehend. They'll be shaped by experiences we've never had, challenges we've never faced, and an environment that's utterly alien to anything in human history. This isn't necessarily a problem to be solved. It might be an inevitable part of becoming an interstellar species. Evolution doesn't just apply to biological systems. It applies to cultures, technologies, and ways of thinking. The humans who spread among the stars will necessarily evolve, both biologically and culturally, in response to their new environments. But this evolutionary pressure works both ways. As we prepare for interstellar exploration, we're already changing ourselves in response to the challenge. The technologies we're developing for space exploration are reshaping life on Earth. The international cooperation required for large space projects is creating new models for global collaboration. The long-term thinking necessary for interstellar missions is influencing how we approach problems like climate change and resource management. In a very real sense, becoming an interstellar species is already changing what it means to be human. We're developing capabilities our ancestors never possessed, thinking in timescales that exceed individual lifespans, and taking on challenges that require unprecedented levels of cooperation and commitment. The economic implications of this transformation are equally profound. The space economy is already worth hundreds of billions of dollars and growing exponentially. Companies are making serious money from satellite communications, Earth observation, space tourism, and asteroid mining research. But this is just the beginning. If we successfully develop the technologies needed for interstellar travel, we'll create economic opportunities that dwarf anything in human history. The resources contained in just one asteroid could exceed the entire wealth of nations. The energy sources we'll need for interstellar propulsion could revolutionize how we power our civilization. The manufacturing techniques developed for space-based construction could transform every industry on Earth. But perhaps more importantly, the pursuit of interstellar capabilities is driving innovations that are already changing life on Earth in unexpected ways. The miniaturization required for interstellar probes is advancing computer technology. The life support systems needed for long-duration space missions are improving environmental technology. The communication systems required for interstellar distances are enhancing global connectivity. This pattern of space exploration driving terrestrial innovation has been consistent throughout history. The Apollo program didn't just put humans on the moon. It created technologies that enabled modern computing, advanced material science, and revolutionized manufacturing. The same pattern is likely to repeat with interstellar exploration, but on an even larger scale. The challenges of interstellar travel are so extreme that solving them will require breakthroughs in virtually every field of human knowledge: physics, engineering, biology, psychology, sociology, economics, philosophy. Every discipline will need to contribute to making interstellar exploration possible. And every breakthrough we make in service of that goal will have applications that extend far beyond space travel. Consider the energy problem. To accelerate even a small spacecraft to a significant fraction of light speed requires energy sources that are orders of magnitude more powerful than anything we currently possess. Solving this problem will likely require mastering fusion power, developing more efficient solar collection systems, or even learning to harness more exotic energy sources. But these same energy technologies could solve the climate crisis, provide abundant clean power for developing nations, and enable technological capabilities we can barely imagine. The pursuit of interstellar travel could inadvertently solve some of humanity's most pressing problems right here on Earth. The same logic applies to every other challenge we face in interstellar exploration. The closed-loop life support systems needed for generation ships could revolutionize agriculture and environmental management right here on our planet. The artificial intelligence required for autonomous interstellar probes could solve problems in medicine, education, and scientific research that seem intractable today. The materials science needed for spacecraft that can survive decades in interstellar space could create stronger, lighter, more durable materials for every conceivable application. We're not just building the capability to reach other stars. We're building the capability to create a fundamentally better civilization wherever we happen to be. But this raises a fascinating question about the nature of interstellar expansion. If the technologies we develop for interstellar travel make life in our solar system dramatically better, will we still want to leave? Or will our solar system become so abundant, so comfortable, so filled with opportunities that interstellar travel becomes unnecessary? This isn't a rhetorical question. Some researchers argue that advanced civilizations might naturally turn inward rather than expanding outward. If you can create virtual worlds indistinguishable from reality, if you can modify your consciousness to experience any imaginable environment, if you can access unlimited energy and resources within your home star system, why would you bother with the enormous effort and risk of interstellar travel? This possibility suggests that truly advanced civilizations might focus on intensive development rather than extensive expansion. Instead of spreading across the galaxy, they might create increasingly sophisticated virtual environments, upload their consciousness to digital systems, or even manipulate matter at the quantum level to create whatever experiences they desire. From this perspective, our current dreams of interstellar expansion might be a temporary phase in our development. We might eventually discover that everything we could possibly want to experience or achieve can be accomplished more easily by transforming ourselves and our local environment, rather than traveling to distant stars. But even if this turns out to be true, the pursuit of interstellar capability might still be worthwhile. The technologies and perspectives we develop in attempting to become an interstellar species will be valuable regardless of whether we actually need to leave our solar system. The journey toward interstellar capability is already making us more capable, more cooperative, and more conscious of our place in the universe. There's another possibility that's even more intriguing. What if the process of developing interstellar technology reveals that the universe is far more connected than we currently understand? What if the same advances that make interstellar travel possible also reveal new ways to communicate or even travel instantaneously across vast distances? Physics is already hinting at connections that transcend our everyday understanding of space and time. Quantum entanglement allows particles to influence each other instantaneously across any distance. The structure of space-time itself might contain shortcuts that could make interstellar travel far easier than we imagine. The nature of consciousness might turn out to be more fundamental to reality than we currently believe. As we push the boundaries of technology in pursuit of interstellar capability, we might discover that the universe works in ways that make our current challenges obsolete. We might find that consciousness can be transmitted instantaneously across any distance, that space-time can be folded to bring distant stars within easy reach, or that reality itself can be manipulated in ways that eliminate the need for physical travel altogether. These possibilities might sound like science fiction, but they're grounded in serious scientific speculation. Physicists are already exploring concepts like wormholes, warp drives, and quantum teleportation. While these ideas remain highly speculative, they illustrate how our understanding of what's possible continues to evolve as our knowledge deepens. The point isn't that any particular exotic technology will solve the interstellar travel problem. The point is that our current understanding of physics and consciousness is incomplete, and the gaps in our knowledge might contain solutions we haven't yet imagined. This uncertainty is actually one of the most exciting aspects of the interstellar challenge. We're not just trying to solve a well-defined engineering problem. We're pushing into territory where our fundamental assumptions about reality might need to be revised. Every step forward in our capability to explore space is also a step forward in our understanding of the universe itself. And this brings us to perhaps the most profound aspect of the question of whether we'll ever leave our solar system. The answer matters less than the asking. The very process of seriously attempting to become an interstellar species is transforming us in ways that might be more important than actually reaching other stars. We're learning to think in cosmic timescales, to cooperate on projects that exceed individual lifespans, to solve problems that require the combined efforts of multiple disciplines and nations. We're developing technologies that could solve existential problems, perspectives that could help us navigate complex global challenges, and capabilities that could enable entirely new forms of civilization. Whether we eventually establish colonies around distant stars might be less important than the fact that we're becoming the kind of species capable of seriously attempting such projects. The transformation is already underway, and it's already changing everything about how we understand ourselves and our place in the universe. The children growing up today will live in a world where interstellar missions are not just science fiction, but active engineering projects. They'll think differently about time, space, and human potential, because they'll grow up knowing that humans are actively working to reach other stars. That shift in perspective might be more transformative than any particular technological breakthrough. We're at a unique moment in human history where the impossible is becoming merely difficult. The question of whether we'll ever leave our solar system is evolving from philosophical speculation to practical planning, and regardless of how that planning ultimately unfolds, the very fact that we're taking it seriously is already changing what it means to be human. The universe is vast, ancient, and filled with wonders we're only beginning to imagine. Whether we explore it by sending our bodies, our minds, or our creations across interstellar distances, the exploration itself is expanding our consciousness, our capabilities, and our understanding of what's possible. We may not yet know whether we'll ever leave our solar system, but we're discovering that asking the question seriously is already taking us places we've never been before. And perhaps that's the most important journey of all. The next few decades will likely determine not just whether interstellar travel is possible, but what form it will take and how it will transform us along the way. We're not just building spaceships, we're building the future of human consciousness itself. And that future is arriving faster than most people realize. The technologies, institutions, and perspectives we need for interstellar exploration are already under development. The only question remaining is how quickly we can bring them together into a coherent program for expanding beyond our solar system. The answer to that question will determine not just where humanity goes next, but what humanity becomes in the process of getting there. The timeline we're looking at for this transformation is both thrilling and sobering. Conservative estimates suggest that meaningful interstellar missions, even robotic ones, are still decades away. But here's what's remarkable about our current moment in history. We're living through the foundational years of what could become humanity's greatest adventure. The decisions we make today about space exploration funding, international cooperation, and technological priorities will directly determine whether our children or grandchildren witness the first successful interstellar mission. Consider the accelerating pace of change in space technology. Just 20 years ago, the idea of reusable rockets was considered impractical by most experts. Today, companies routinely land rockets back on Earth and reuse them for multiple missions. The James Webb Space Telescope, launched just a few years ago, is already revolutionizing our understanding of distant worlds and the conditions that might support life around other stars. Private companies are seriously planning missions to asteroids, the Moon, and Mars, with timelines that seemed impossibly aggressive just a decade ago. This acceleration isn't just about individual technologies improving. It's about entire technological ecosystems reaching maturity simultaneously. Artificial intelligence is approaching levels of sophistication that could enable truly autonomous spacecraft operations. Advanced materials science is producing substances that are stronger, lighter, and more radiation resistant than anything previous generations could imagine. Energy storage and generation technologies are becoming more efficient and compact every year, but perhaps most importantly, we're witnessing the emergence of a space-focused economy that could eventually support the massive investments required for interstellar missions. When companies can make money from space tourism, asteroid mining, and orbital manufacturing, they create the economic foundation that could eventually fund far more ambitious projects. The space economy isn't just growing. It's becoming self-sustaining in ways that government-funded programs never could. This economic transformation is crucial because interstellar missions will require investment levels that exceed what any single nation could reasonably commit to. But if space-based industries become profitable enough, if the potential returns from interstellar exploration become clear enough, private capital might eventually flow toward these projects, just as it flows toward any other promising investment opportunity. The psychological barriers to interstellar exploration are proving to be just as significant as the technological ones. Human beings evolved to care most about immediate threats and opportunities. Our brains are wired to focus on problems we can solve within our lifetimes, challenges that affect our families and communities directly. Asking people to commit resources to projects that might take centuries to complete goes against some of our deepest psychological instincts. Yet we're already seeing signs that this psychological barrier isn't insurmountable. Climate change has taught us to think in longer timescales, to consider problems that might affect our children and grandchildren, rather than just ourselves. The space industry has demonstrated that people will invest in projects with uncertain timelines if the potential returns are significant enough. More intriguingly, younger generations seem naturally more comfortable with long-term thinking and global cooperation than their predecessors. People who grew up with the internet, who communicate routinely with individuals on other continents, who see images from Mars rovers and space telescopes as part of their daily news cycle, approach questions about interstellar exploration with a fundamentally different mindset than previous generations. These psychological shifts might be just as important as technological advances in making interstellar missions possible. If enough people genuinely believe that human expansion beyond our solar system is both necessary and achievable, the social and political support for such projects becomes much more likely. The scientific discoveries we're making about other star systems are also changing the conversation in profound ways. Every new exoplanet we discover, every potentially habitable world we identify around nearby stars, makes the case for interstellar exploration more compelling. We're not just talking about sending probes into empty space anymore. We're talking about investigating specific worlds that might harbor life, that might be suitable for human habitation, that might hold answers to fundamental questions about the nature and prevalence of life in the universe. The Kepler Space Telescope and its successors have revealed that planets are incredibly common throughout our galaxy. Nearly every star we can observe has at least one planet orbiting it, and many of these worlds fall within the temperature ranges where liquid water could exist. Some of these potentially habitable planets orbit stars that are very close to us in astronomical terms. Proxima Centauri b, just over 4 light-years away, might have conditions suitable for life. TRAPPIST-1, about 40 light-years distant, hosts multiple Earth-sized worlds in its habitable zone. These discoveries transform interstellar exploration from abstract scientific curiosity to concrete investigation of specific targets. We're not just asking whether we can build machines capable of reaching other stars. We're asking whether we can build machines capable of studying potentially habitable worlds that we know exist around those stars. The biological implications of interstellar travel are becoming clearer as we learn more about how space affects human physiology. Long-duration missions aboard the International Space Station are teaching us about bone density loss, muscle atrophy, radiation exposure, and psychological stress in ways that directly inform planning for interstellar journeys. We're discovering which problems can be solved with current technology and which will require fundamental breakthroughs. Some of the challenges are more manageable than we initially feared. Artificial gravity generated by rotating spacecraft sections could eliminate many of the bone and muscle problems associated with weightlessness. Advanced shielding materials could protect crews from most forms of radiation. Closed-loop life support systems are already being tested that could theoretically sustain crews for decades without resupply. Other challenges are proving more intractable. The psychological stress of permanent separation from Earth, the social dynamics of small groups confined together for extended periods, the medical challenges of treating serious illnesses without possibility of evacuation. These human factors might ultimately than any technological prove more limiting constraint. But even these seemingly insurmountable problems are driving innovations that extend far beyond space exploration. Research into psychological resilience for space crews is advancing our understanding of mental health in extreme environments. Work on medical systems for interstellar missions is pushing the boundaries of automated surgery and diagnostic equipment. Studies of social dynamics in isolated groups are revealing principles that apply to everything from military units to corporate teams. The philosophical implications of interstellar exploration are perhaps the most profound of all. If we successfully establish human settlements around other stars, we'll be creating the first truly independent human societies in history. Every previous human expansion, from the settlement of remote islands to the colonization of new continents, has maintained some connection to the broader human community. But interstellar colonies would be genuinely isolated, forced to develop their own solutions to fundamental questions about governance, economics, culture, and meaning. This independence isn't just practical, it's existential. The humans who settle around other stars will face challenges and opportunities that no one on Earth has ever experienced. They'll need to develop new ways of thinking about identity, community, and purpose. Over time, they might evolve culturally and even biologically in directions we can't predict. This prospect of human diversification across multiple star systems raises questions that touch on the deepest aspects of what it means to be human. Will the descendants of interstellar colonists still consider themselves human in the same sense we do? Will they maintain connections to Earth-based humanity? Or will they develop into something genuinely new? Are we looking at the next step in human evolution, or the beginning of multiple human species? These aren't just philosophical abstractions. They're practical questions that will need answers if we're serious about interstellar colonization. How do we maintain communication and cooperation between human settlements separated by light years? How do we prevent interstellar colonies from developing into threats to Earth or each other? How do we ensure that the expansion of humanity beyond our solar system serves the interests of all human beings, not just those wealthy or fortunate enough to participate directly? The governance challenges alone are staggering. What legal frameworks apply to interstellar colonies? Who has jurisdiction over human settlements around other stars? How do we prevent the same patterns of exploitation and conflict that have characterized human expansion throughout history from repeating themselves on an interstellar scale? These questions are becoming more than academic as space law evolves to address the realities of commercial space exploration. The legal frameworks we develop for asteroid mining, lunar settlements, and Mars colonies will likely serve as precedents for interstellar governance. We're essentially writing the constitution for human expansion beyond Earth, even though we don't fully realize it yet. The environmental implications of becoming an interstellar species are equally complex. On one hand, spreading human civilization across multiple star systems could serve as the ultimate backup plan for preserving both human culture and Earth's biological heritage. If catastrophe strikes our home planet, interstellar colonies could ensure that the legacy of Earth-based life continues elsewhere in the galaxy. On the other hand, interstellar expansion could also represent the ultimate environmental impact. If we carry Earth life to other star systems, we might be contaminating pristine environments that have followed completely different evolutionary paths for billions of years. We might be imposing Earth-based biology on worlds that harbor their own unique forms of life. These concerns are already shaping how we plan even robotic missions to other stars. Planetary protection protocols are being developed to minimize the risk of contaminating potentially habitable worlds with Earth-based microorganisms. But the ethical questions become far more complex when we're talking about deliberate colonization efforts rather than just scientific exploration. Do we have the right to establish human settlements on worlds that might harbor indigenous life? How do we balance human expansion needs against the preservation of alien ecosystems? What responsibilities do we have to future generations of both humans and potential alien life forms? The answers to these questions will likely determine not just whether we leave our solar system, but how we do it and what kind of interstellar civilization we create in the process. The choices we make about these issues will define the character of humanity's cosmic future for potentially millions of years. But perhaps the most remarkable aspect of our current situation is how rapidly our perspective on these questions is evolving. Ideas that seemed like pure science fiction just decades ago are now subjects of serious academic research and policy discussion. Graduate students are writing dissertations on interstellar mission agencies, are funding research into technologies design. Government that could enable interstellar exploration. Private organizations are investing real money in projects specifically designed to advance interstellar capabilities. This shift from speculation to serious planning represents a fundamental change in how humanity sees itself and its future. We're no longer just a species that happens to live on one planet. We're beginning to see ourselves as a species with the potential to spread throughout the galaxy to become a truly cosmic civilization. That transformation in self-perception might be the most important factor in determining whether we actually achieve interstellar capabilities. People who see interstellar expansion as an inevitable part of human development will make different choices, support different policies, and invest in different technologies than people who see it as an impossible dream. The generation that's growing up today will be the first to make major life decisions with the genuine possibility of interstellar missions in their lifetimes. Some of them will choose careers in space technology specifically because they want to contribute to interstellar exploration. Some will support political candidates based partly on their positions on space exploration funding. Some will make investment decisions with interstellar commercial opportunities in mind. These individual choices, multiplied across millions of people, will collectively determine whether we develop the social, economic, and technological infrastructure needed for interstellar missions. The future of interstellar exploration isn't just being determined in government laboratories and corporate boardrooms. It's being shaped by the choices that ordinary people make every day about what kind of future they want to support. And those choices are being influenced by our growing understanding of just how extraordinary and precious our situation really is. The more we learn about the universe, the more we realize how remarkable it is that complex life evolved on Earth at all. The conditions that allowed for the development of intelligence, technology, and civilization represent an almost impossibly unlikely convergence of factors. This realization creates both urgency and responsibility around the question of interstellar expansion. If intelligent life is as rare as it appears to be, then we might have obligations that extend far beyond our own species. We might be responsible not just for ensuring human survival, but for preserving and spreading the phenomenon of consciousness itself throughout the galaxy. From this perspective, interstellar exploration isn't just about human expansion or scientific curiosity. It's about ensuring that the universe continues to have conscious beings capable of appreciating its beauty, understanding its complexity, and perhaps even improving upon its natural processes. Whether we'll ever leave our solar system might ultimately depend on whether we can embrace this level of cosmic responsibility. If we can see ourselves not just as one species among many, but as the universe's best current hope for conscious exploration and understanding, we might find the motivation and resources needed to make interstellar expansion not just possible, but inevitable. The question isn't really whether we'll ever leave our solar system. The question is whether we'll choose to become the kind of species capable of doing so responsibly, sustainably, and in service of something larger than our immediate self-interest. That choice is being made right now in the decisions we make about science funding, international cooperation, environmental protection, and technological development. Every choice that expands human capability, promotes long-term thinking, or advances our understanding of the universe brings us closer to becoming an interstellar civilization. The transformation has already begun. We just don't know yet how far it will take us, or what we'll discover about ourselves and the universe along the way. But here's what's becoming increasingly clear as we examine the actual mechanics of how interstellar travel might work. The solutions emerging from laboratories and research facilities around the world are stranger and more beautiful than anything we could have imagined just decades ago. Scientists are discovering that the vacuum of space isn't actually empty at all. It's filled with quantum fluctuations, virtual particles that pop in and out of existence, energy fields that permeate everything. Some researchers believe these phenomena might be harnessed for propulsion in ways that sidestep our current understanding of rocket physics entirely. Imagine a spacecraft that doesn't push against anything, but instead manipulates the structure of space-time itself. The Alcubierre drive, named after physicist Miguel Alcubierre, proposes exactly this. By contracting space in front of a vessel and expanding it behind, you could create a bubble of warped space-time that moves faster than light, without the spacecraft itself ever exceeding light speed. The mathematics work out. The physics are consistent with general relativity. The energy requirements remain astronomical, but researchers are finding ways to reduce them from requiring the mass of Jupiter to something potentially achievable with advanced fusion technology. This isn't idle speculation anymore. Research groups are conducting actual experiments, testing whether space-time manipulation might be possible with technologies we could develop in the coming decades. The results remain preliminary, but the fact that serious scientists are pursuing these investigations represents a fundamental shift in how we approach the interstellar challenge. Meanwhile, advances in quantum mechanics are opening up possibilities that sound like they belong in fantasy rather than physics. Quantum entanglement, that spooky action at a distance that bothered Einstein so much, might provide pathways for communication that transcend the light speed barrier. If we can learn to reliably create and maintain entangled quantum states across vast distances, we might be able to communicate with interstellar missions instantaneously. No more waiting years for signals to cross the void between stars. No more isolation for spacecraft venturing into the unknown. Some physicists are even exploring whether quantum entanglement might provide clues about the fundamental nature of space and time themselves. If particles can remain connected regardless of distance, what does that tell us about the structure of reality? Could there be deeper levels of connection in the universe that we're only beginning to perceive? These questions push us toward a radically different understanding of what it might mean to travel between stars. If consciousness itself turns out to be a quantum phenomenon, if information can be transmitted through channels we don't yet understand, then the nature of interstellar exploration might be completely different from our current assumptions. Consider the possibility of consciousness uploading. If we can map human consciousness with sufficient precision, if we can capture the patterns of thought and memory that constitute individual identity, then we might be able to transmit that information at the speed of light to receivers around other stars. The physical journey would still take years, but from the perspective of the traveling consciousness, the transition would be instantaneous. Close your eyes in one solar system, open them in another. Your body would be reconstructed from local materials at the destination, but your mind, your memories, your essential self would remain continuous. This possibility exists at the intersection of neuroscience, quantum physics, and philosophy. We're making progress on all three fronts simultaneously. Brain imaging technology is reaching resolutions where individual neurons and their connections can be mapped. Artificial intelligence is approaching sophistication levels where simulating aspects of consciousness becomes feasible. Our understanding of what consciousness actually is continues to deepen in ways that suggest it might be far more fundamental to reality than we previously believed. Even if consciousness uploading proves impossible or undesirable, the same advances are opening other pathways for interstellar exploration. Genetic engineering and biological enhancement could create humans modified to survive the rigors of interstellar travel. Extended lifespans through cellular rejuvenation could make century-long journeys feasible within individual human lives. Psychological adaptations could make decades-long confinement not just survivable, but fulfilling. The biological technologies needed for such enhancements are developing alongside the physical technologies for interstellar propulsion. Gene editing is becoming precise enough to make targeted modifications to human physiology. Synthetic biology is learning to design organisms from scratch for specific environments and purposes. These advances suggest that the humans who eventually travel to other stars might be fundamentally different from the humans alive today. Not because they'll be forced to adapt, but because they'll choose to optimize themselves for the unique challenges and opportunities of interstellar exploration. They might live longer, think differently, experience reality in ways that are enhanced compared to our current biological limitations. This isn't science fiction anymore. It's emerging capability that's being developed right now in laboratories around the world. But perhaps the most intriguing development is the growing recognition that we might not need to solve the distance problem at all. Instead of bringing human beings to other stars, we might eventually bring other stars closer to us through technologies that manipulate space and time in ways that effectively reduce the distances involved. Wormholes, those hypothetical tunnels through space-time that could connect distant regions of the universe, remain purely theoretical. But the mathematics describing them are consistent with our understanding of physics. Some researchers are exploring whether such structures might be created artificially, or whether natural wormholes might exist and be detectable. Even more speculative are proposals for manipulating the fundamental constants of physics within localized regions of space. If the speed of light could be increased within a spacecraft's immediate vicinity, or if time could be dilated in ways that make long journeys pass quickly from the traveler's perspective, then interstellar exploration might become routine. These possibilities remain far beyond our current technological capabilities, but they illustrate how rapidly our understanding of what might be possible continues to evolve. Each new discovery in fundamental physics opens up potential applications that previous generations couldn't have imagined. The same pattern that gave us nuclear power, lasers, and computer technology from advances in quantum mechanics might eventually give us interstellar travel capabilities from advances in our understanding of space-time, consciousness, and the relationship between information and reality. What's particularly fascinating is how these various technological streams are beginning to converge in unexpected ways. Artificial intelligence research is informing our understanding of consciousness and cognition. Quantum computing is revealing new approaches to information processing that might apply to brain function. Advances in materials science are creating substances that could serve as both spacecraft components and biological enhancement materials. This convergence is being accelerated by economic incentives that extend far beyond space exploration. The same technologies that might enable interstellar travel are creating new industries, solving pressing problems on Earth, and generating returns on investment that fund further research and development. We're not just building capabilities for interstellar exploration, we're building capabilities that transform every aspect of human civilization. The timeline for when these converging technologies might enable practical interstellar missions remains uncertain, but the pace of progress is accelerating in ways that consistently surprise experts. Developments that were predicted to take decades are happening in years. Capabilities that seemed impossible just a few years ago are becoming routine parts of our technological landscape. Consider how our relationship with artificial intelligence has evolved in just the past few years. Systems that can engage in sophisticated conversations, create original works, and solve complex problems are becoming commonplace. These same systems are being applied to spacecraft design, mission planning, and the autonomous operation of complex systems in space. The artificial intelligence that might eventually pilot interstellar missions is already being tested and refined in applications much closer to home. Similarly, our ability to manipulate matter at molecular and atomic levels is advancing at unprecedented rates. Nanotechnology that once existed only in theoretical papers is now being used to create materials with properties that seem almost magical. Self-assembling structures, programmable matter, and molecular machines are transitioning from laboratory curiosities to practical applications. These advances are particularly relevant to interstellar exploration because they address some of the most fundamental challenges of long-duration space missions. Spacecraft that can repair and maintain themselves, materials that can adapt their properties to changing conditions, manufacturing systems that can create whatever is needed from available resources, could make interstellar missions far more feasible than current technologies suggest. But beyond the technological capabilities, we're also developing the social and institutional frameworks that could support interstellar exploration projects. The international cooperation that's making large-scale scientific collaborations possible is creating precedents for the kind of global coordination that interstellar missions would require. Private space companies are demonstrating that ambitious space projects can be sustained and scaled through commercial incentives rather than just government funding. The space economy is creating revenue streams that could eventually support much more ambitious projects than anything government agencies could fund independently. Most importantly, younger generations are growing up with fundamentally different assumptions about what's possible and what's worth pursuing. People who have never known a world without space stations, Mars rovers, and routine commercial space flights approach questions about interstellar exploration with a sense of possibility rather than impossibility. This generational shift in perspective might be the most important factor in determining whether we actually achieve interstellar capabilities. Technical challenges can be solved with sufficient time and resources, but only if there's sustained social and political support for solving them. That support is most likely to come from people who see interstellar exploration not as science fiction, but as a natural extension of capabilities we're already developing. The children growing up today will be the ones making major decisions about resource allocation, research priorities, and international cooperation in the coming decades. If they see interstellar exploration as both desirable and achievable, they'll make choices that support its development. If they see it as unnecessary or impossible, they'll direct their attention and resources elsewhere. The stories we tell ourselves about humanity's cosmic future are therefore not just philosophical abstractions. They're practical factors that influence real-world decisions about everything from education policy to research funding to international agreements about space exploration. This is why the question of whether we'll ever leave our solar system is so important. Regardless of what the ultimate answer turns out to be, the very process of seriously considering the question is shaping how we understand ourselves, our capabilities, and our responsibilities as conscious beings in a vast and mysterious universe. We're discovering that becoming the kind of species capable of interstellar exploration requires us to become better at everything. More cooperative, more patient, more technically sophisticated, more environmentally responsible, and more conscious of our long-term impact on the cosmos. These improvements are valuable whether or not we ever actually travel to other stars. The pursuit of interstellar capability is therefore not just about reaching distant destinations. It's about reaching higher levels of human potential. It's about becoming worthy of the cosmic stage on which we find ourselves performing. And in that sense, we're already succeeding. The technologies we're developing, the institutions we're building, the perspectives we're gaining, and the cooperation we're achieving in pursuit of interstellar exploration are already transforming human civilization in profound ways. Whether we'll ever leave our solar system remains an open question, but we're already becoming the kind of species that could do so responsibly and successfully, and that transformation might be the most important journey of all, regardless of where it ultimately takes us among the stars. The future of human expansion beyond our solar system won't be determined by any single breakthrough or decision. It will emerge from the accumulated choices of billions of people over the coming decades, each contributing their skills, resources, and dreams to the collective human project of understanding and exploring our cosmic environment. That project is already underway, accelerating with each passing year, carrying us toward possibilities that seemed impossible just a generation ago. Think about what's happening right now in research facilities scattered across our planet. Scientists are making discoveries about the nature of space itself that could fundamentally alter how we approach the interstellar challenge. The vacuum of space, once thought to be empty, is revealing itself to be a dynamic medium filled with energy fluctuations and phenomena that might be harnessed for propulsion. Theoretical physicists are exploring concepts that wouldn't move a spacecraft through space at all, but would instead manipulate the fabric of space-time itself. These aren't just mathematical curiosities anymore. Research groups are conducting actual experiments to test whether space-time manipulation might be achievable with technologies we could develop in the coming decades. The results remain preliminary. The energy requirements remain staggering. But the mere fact that serious scientists are pursuing these investigations represents a fundamental shift in how we approach the problem. Meanwhile, advances in quantum mechanics are revealing connections between consciousness, information, and the structure of reality that could open entirely new pathways for interstellar exploration. If consciousness turns out to be more fundamental to the universe than we currently understand, if information can be transmitted across vast distances through quantum channels, then the nature of what it means to travel to other stars might be completely different from our current assumptions. Imagine being able to map human consciousness with sufficient precision that the information pattern constituting your mind could be transmitted at the speed of light to a receiver around another star. The physical journey would still take years, but from your subjective experience, you would simply close your eyes in one location and open them in another. Your body might be artificially constructed from local materials at the destination, but your consciousness, your memories, your essential self would remain continuous. This possibility pushes us into territory where science and philosophy merge, where questions about the nature of identity and existence become as important as questions about propulsion and radiation shielding. But the underlying technologies that might make such scenarios possible are advancing rapidly. Brain imaging is reaching resolutions that allow researchers to map individual neurons and their connections. Artificial intelligence is approaching levels where simulating aspects of consciousness becomes feasible. Quantum computing is revealing new ways to process information that transcend classical limitations. Even if consciousness uploading proves impossible, the same advances in understanding the relationship between mind and matter are opening up other possibilities for interstellar exploration. Enhanced human beings, modified to survive the rigors of interstellar travel, could be designed with extended lifespans, improved radiation resistance, and psychological adaptations that make decades-long journeys not just survivable, but fulfilling. The biological technologies needed for such enhancements are developing alongside the physical technologies for interstellar propulsion. Gene editing is becoming precise enough to make targeted modifications to human physiology. Synthetic biology is learning to design organisms from scratch for specific environments and purposes. Nanotechnology is approaching the capability to repair and maintain biological systems at the molecular level. These advances suggest that the humans who eventually travel to other stars might be fundamentally different from the humans alive today. Not because they'll be forced to adapt to alien environments, but because they'll choose to optimize themselves for the unique challenges and opportunities of interstellar exploration. They might live longer, think differently, and experience reality in ways that are enhanced compared to our current biological limitations. But perhaps the most intriguing development in our approach to interstellar exploration is the growing recognition that we might not need to solve the distance problem at all. Instead of bringing human beings to other stars, we might eventually bring other stars closer to us through technologies that manipulate space and time in ways that effectively reduce the distances involved. Wormholes, those hypothetical tunnels through space-time that could connect distant regions of the universe, remain purely theoretical, but the mathematics that describe them are consistent with our current understanding of physics. Some researchers are exploring whether such structures might be created artificially, or whether natural wormholes might exist and be detectable. Even more speculative are proposals for manipulating the fundamental constants of physics within localized regions of space. If the speed of light could be increased within a spacecraft's immediate vicinity, or if time could be dilated in ways that make long journeys pass quickly from the traveler's perspective, then interstellar exploration might become as routine as intercontinental travel is today. These possibilities remain far beyond our current technological capabilities, but they illustrate how rapidly our understanding of what might be possible continues to evolve. Each new discovery in fundamental physics opens up potential applications that previous generations couldn't have imagined. The same pattern that gave us nuclear power and computer technology from advances in quantum mechanics might eventually give us interstellar travel capabilities from advances in our understanding of space-time and the relationship between information and reality. What's particularly fascinating about our current situation is how these various technological streams are beginning to converge in unexpected ways. Artificial intelligence research is informing our understanding of consciousness. Quantum computing is revealing new approaches to information processing. Advances in material science are creating substances that could serve as both spacecraft components and biological enhancement materials. This convergence is being accelerated by economic incentives that extend far beyond space exploration. The same technologies that might enable interstellar travel are creating new industries, solving pressing problems here on Earth, and generating returns that fund further research and development. We're not just building capabilities for interstellar exploration, we're building capabilities that transform every aspect of human civilization. The timeline for when these converging technologies might enable practical interstellar missions remains uncertain, but the pace of progress is accelerating in ways that consistently surprise experts. Developments that were predicted to take decades are happening in years. Capabilities that seemed impossible just a few years ago are becoming routine parts of our technological landscape. Consider how our relationship with artificial intelligence has evolved in just the past few years. Systems that can engage in sophisticated conversations and solve complex problems are becoming commonplace. These same systems are being applied to spacecraft design and mission planning. The artificial intelligence that might eventually manage interstellar missions is already being tested in applications much closer to home. Similarly, our ability to manipulate matter at molecular and atomic levels is advancing at unprecedented rates. Nanotechnology that once existed only in theoretical papers is now being used to create materials with properties that seem almost magical. Self-assembling structures and programmable matter are transitioning from laboratory curiosities to practical applications. These advances are particularly relevant to interstellar exploration because they address some of the most fundamental challenges of long-duration space missions. Spacecraft that can repair themselves, materials that adapt their properties to changing conditions, manufacturing systems that can create whatever is needed from available resources could make interstellar missions far more feasible than current technologies suggest. But beyond the technological capabilities, we're also developing the social and institutional frameworks that could support interstellar exploration projects. The international cooperation that's enabling large-scale scientific collaborations is creating precedents for the kind of global coordination that interstellar missions would require. Private space companies are demonstrating that ambitious space projects can be sustained through commercial incentives, rather than just government funding. The space economy is creating revenue streams that could eventually support much more ambitious projects than anything government agencies could fund independently. Most importantly, younger generations are growing up with fundamentally different assumptions about what's possible. People who have never known a world without space stations and Mars rovers approach questions about interstellar exploration with a sense of possibility rather than impossibility. This generational shift in perspective might be the most important factor in determining whether we actually achieve interstellar capabilities. Technical challenges can be solved with sufficient time and resources, but only if there's sustained social and political support for solving them. That support is most likely to come from people who see interstellar exploration not as fantasy, but as a natural extension of capabilities we're already developing. The children growing up today will be the ones making major decisions about resource allocation and research priorities in the coming decades. If they see interstellar exploration as both desirable and achievable, they'll make choices that support its development. The stories we tell ourselves about humanity's cosmic future are therefore not just philosophical abstractions. They're practical factors that influence real-world decisions about everything from education policy to research funding. This is why the question of whether we'll ever leave our solar system matters so much. Regardless of what the ultimate answer turns out to be, the very process of seriously considering the question is shaping how we understand ourselves and our responsibilities as conscious beings in a vast universe. We're discovering that becoming the kind of species capable of interstellar exploration requires us to become better at everything. More cooperative, more patient, more technically sophisticated, more conscious of our long-term impact on the cosmos. These improvements are valuable whether or not we ever actually travel to other stars. The pursuit of interstellar capability is therefore not just about reaching distant destinations. It's about reaching higher levels of human potential. It's about becoming worthy of the cosmic stage on which we find ourselves. And in that sense, we're already succeeding. The technologies we're developing, the institutions we're building, the perspectives we're gaining are already transforming human civilization in profound ways. Whether we'll ever leave our solar system remains an open question, but we're already becoming the kind of species that could do so responsibly and successfully. That transformation might be the most important journey of all, regardless of where it ultimately takes us among the stars. The question isn't whether we're capable of leaving our solar system. The question is, what we'll discover about ourselves and the universe in the process of trying. The answer to that question is already being written in the choices we make today, in the technologies we pursue, and in the dreams we're bold enough to imagine into reality. And as we'll discover, those choices are revealing something extraordinary about the nature of human consciousness itself. There's something happening right now that most people don't fully grasp. While we've been debating whether interstellar travel is possible, whether we have the technology or the resources, something much more profound has been taking place. We've been transforming ourselves into the kind of beings who ask these questions seriously. And that transformation might be more important than any spacecraft we could ever build. Think about it for a moment. You're contemplating journeys that would span centuries, considering technologies that manipulate the very fabric of space and time, imagining futures where human consciousness itself might travel between stars at the speed of light. Your ancestors, just a few generations ago, couldn't have conceived of such possibilities. Not because they lacked imagination, but because the conceptual framework for thinking about these problems simply didn't exist. We're living through the emergence of what we might call cosmic consciousness, a way of thinking that naturally encompasses stellar distances, geological timescales, and technological possibilities that transcend biological limitations. This isn't just academic knowledge we acquire through education. It's becoming part of how we instinctively understand our place in the universe. Children today grow up knowing that robots are exploring Mars, that telescopes can see galaxies billions of light years away, that scientists routinely manipulate individual atoms to build new materials. They don't think of these as miraculous achievements. They think of them as the normal baseline of human capability. For them, the question isn't whether we can do extraordinary things. The question is which extraordinary things we should choose to do. This shift in baseline expectations is accelerating in ways that surprise even the experts who study technological development. The same artificial intelligence systems that can engage in sophisticated conversations are being integrated into spacecraft design. The same genetic engineering techniques that can modify organisms to thrive in extreme environments are being applied to enhancing human capability for space travel. But perhaps most remarkably, these advances aren't happening in isolation. They're part of an interconnected web of technological and social development that's creating capabilities none of us anticipated. The private space industry that's driving down launch costs is also creating the economic foundation for much more ambitious projects. The international cooperation that's enabling large-scale scientific collaborations is building the institutional frameworks we'll need for interstellar missions. The result is a feedback loop where each advance enables others, where progress in one area accelerates development in seemingly unrelated fields, where the timeline for achieving what once seemed impossible keeps compressing in ways that confound our expectations. We're moving away from visions of massive starships carrying thousands of people toward more realistic scenarios involving smaller, more focused missions that build capability over time. The first true interstellar missions will likely be robotic probes, but more capable and sophisticated than anything we've built before. These missions will teach us about the interstellar environment, test technologies for communication across vast distances, and possibly even begin preparing other star systems for eventual human presence. Following these initial probes, we might see waves of increasingly sophisticated missions, automated manufacturing systems that could begin building infrastructure around other stars, biological samples that could begin terraforming potentially habitable worlds. Eventually, perhaps human crews that could establish permanent settlements. This step-by-step approach makes interstellar exploration seem less like an impossible dream and more like a natural extension of what we're already doing. We're not trying to solve every problem at once. We're building capabilities systematically, learning from each mission, using each success to enable the next more ambitious goal. And here's what makes this approach so compelling. We don't need to wait for revolutionary breakthroughs to get started. The technologies we need for the first steps already exist or are in development. We could launch interstellar precursor missions within the next few decades using extensions of current technology. Each of these missions would teach us something new about the challenges of interstellar travel. They would test our ability to communicate across vast distances, to build systems that operate reliably for decades, to navigate in the space between stars. Most importantly, they would maintain momentum and interest in interstellar exploration, keeping the goal alive in public consciousness while we develop the more advanced technologies needed for human missions. The timeline for all of this remains uncertain. Robotic interstellar missions might be possible within 50 years. Human missions might require a century or more. But what's becoming clear is that the question isn't whether we'll ever leave our solar system. The question is how long it will take and what form that expansion will ultimately take. We're already taking the first steps, even if we don't always recognize them as such. Every advance in space technology, every successful long-duration mission, every new discovery about the nature of our universe is bringing us closer to the day when humans will look up at the night sky from the surface of a world orbiting another star. The journey has already begun. We just don't know yet where it will ultimately take us, or what we'll discover about ourselves and the universe along the way. Right now, across every continent on our planet, there are people working on pieces of this puzzle without even realizing how their work connects to the larger picture. A materials scientist in Tokyo is developing polymers that can withstand radiation levels that would kill any living thing. She thinks she's working on better solar panels. What she's actually creating could become the shielding that protects the first interstellar probe from cosmic rays. A software engineer in Mumbai is writing code that allows autonomous systems to make decisions without human input for extended periods. He thinks he's improving warehouse robotics. What he's actually building could become the decision-making framework for spacecraft that will operate for decades without receiving a single command from Earth. A biologist in São Paulo is studying organisms that can survive in the most extreme environments on our planet. She thinks she's researching extremophiles for their own sake. What she's actually uncovering could be the blueprint for biological systems that establish the first foothold of Earth life on worlds we've never seen. This is how transformative change actually happens. Not through grand declarations or single heroic efforts, but through thousands of small advances that accumulate until suddenly the impossible becomes routine. The Manhattan Project didn't start with someone deciding to split the atom. It started with decades of seemingly unrelated research in physics, chemistry, and engineering that only revealed its full potential when brought together under extraordinary circumstances. The same pattern is unfolding right now with interstellar exploration. We're building the foundation one brick at a time, often without recognizing that we're constructing something that will eventually tower over everything humanity has ever attempted. But there's something else happening that's equally important. We're discovering that the technologies enabling interstellar travel are the same technologies that could solve our most pressing problems right here at home. The closed-loop life support systems designed for generationships could revolutionize how we manage resources on a planet struggling with environmental degradation. The energy systems capable of powering interstellar missions could provide clean, abundant power that ends our dependence on fossil fuels. The artificial intelligence needed to manage autonomous spacecraft could help us solve problems in medicine, education, and infrastructure that currently seem intractable. This convergence isn't coincidental. The challenges of surviving for decades or centuries in the hostile environment of space mirror the challenges of creating sustainable civilization on a planet with finite resources. The solutions we develop for one problem naturally apply to the other. Consider the water recycling systems being developed for Mars missions. These systems can purify and reuse water with efficiency levels that exceed 99%. Now imagine deploying that technology in regions of Earth facing water scarcity. Suddenly, interstellar research becomes a pathway to solving terrestrial crises. The same logic applies to food production. Growing crops in the confined spaces of spacecraft requires innovations in vertical farming, nutrient cycling, and crop optimization that could help feed Earth's growing population. The medical technologies designed to diagnose and treat illnesses on spacecraft without access to hospitals could bring advanced healthcare to remote regions of our planet. This dual benefit creates a powerful argument for pursuing interstellar capabilities, even if we never actually send humans to other stars. The journey toward becoming an interstellar species is making us better at being a planetary species first. But let's talk about something that doesn't get discussed enough in conversations about space exploration. The sheer audacity of what we're attempting. We're talking about sending human consciousness, in whatever form that takes, across distances so vast that light itself takes years to traverse them. We're proposing to establish human presence in environments where every single condition is hostile to life as we know it. We're planning projects that will require sustained effort across time periods longer than most human institutions have ever survived. This isn't just ambitious, it's almost absurdly optimistic. And yet, that optimism might be our greatest strength as a species. Throughout history, humans have consistently achieved things that seemed impossible precisely because we were naive enough to try. The Wright brothers didn't have sophisticated wind tunnels or computer simulations. They had curiosity, determination, and a willingness to fail repeatedly until they succeeded. The scientists who put humans on the moon were working with computers less powerful than modern smartphones. What they had was vision and the collective will to make that vision real. We're entering a similar moment now with interstellar exploration. We don't have all the answers. We don't even have all the questions yet, but we have something potentially more valuable. We have a generation of young people who look at the stars and see not distant impossibilities, but future destinations. That shift in perspective changes everything. When going to other star systems stops being science fiction and starts being engineering, when it transitions from fantasy to goal, the entire trajectory of human civilization adjusts to make that goal achievable. Think about how this plays out in education. Students choosing careers in aerospace engineering aren't just thinking about building better airplanes. They're thinking about building the engines that will power interstellar missions. Researchers pursuing advanced degrees in biology aren't just studying life on Earth. They're studying how life might be transported and sustained across interstellar distances. This reorientation of human talent toward cosmic goals is already creating momentum that will be difficult to stop. Every year, thousands of brilliant young minds enter fields related to space exploration and development. They bring with them fresh perspectives, innovative ideas, and most importantly, the assumption that interstellar travel is not just possible, but inevitable. Their professors, shaped by earlier paradigms, might teach them that certain things are impossible. But these students are growing up watching private companies routinely land rockets, seeing rovers explore Mars in real time, and witnessing the discovery of thousands of potentially habitable worlds around other stars. The impossible has become their normal. And that normalization of the extraordinary is perhaps the most powerful force driving us toward interstellar capability. But we need to be honest about the challenges that remain. The psychological dimensions of interstellar travel might prove more difficult than any technical problem. How do you maintain human sanity and social cohesion in a confined space for decades? How do you preserve cultural knowledge and technical expertise across generations? How do you prevent the social dynamics of small, isolated groups from devolving into conflict that could doom entire missions? These aren't abstract questions. NASA and other space agencies are studying them right now through analog missions that simulate long-duration space travel. Research stations in Antarctica, underwater habitats, and isolation chambers are all serving as laboratories for understanding human behavior under conditions that approximate interstellar travel. What we're learning is both encouraging and sobering. Humans are remarkably adaptable. We can maintain psychological health and social cooperation in extreme environments if the conditions are structured correctly. But we're also discovering new challenges we hadn't anticipated. The feeling of Earth always being within reach, even if just as a blue dot in the sky, provides psychological comfort that would be absent during true interstellar voyages. The knowledge that rescue is at least theoretically possible, even if unlikely, changes how people think about risk and isolation. Remove those safety nets, and the psychological landscape transforms entirely. Some researchers believe the solution lies in creating spacecraft environments that feel less like vehicles and more like worlds. Not just metal tubes with life support, but ecosystems with soil, water, plants, and animals. Places where children could be born and raised with some semblance of normal childhood, even if that normal is defined by metal walls and recycled air. Others think the answer involves fundamentally changing human consciousness itself. If we can modify how we experience time, how we process isolation, how we form social bonds, then we might be able to create humans who are psychologically adapted for interstellar travel in ways we currently aren't. These modifications could be technological, perhaps through neural interfaces that allow deeper forms of communication and shared experience. Or they could be biological, using genetic engineering to alter the neurological substrates of social behavior and temporal perception. The ethical implications of such modifications are staggering. Are we talking about creating a new subspecies of humans specifically designed for space travel? Would these modified humans still be us in any meaningful sense? And who makes the decision about what modifications are acceptable? These questions don't have easy answers. They sit at the intersection of biology, ethics, philosophy, and practical necessity. But they're questions we'll need to answer if we're serious about sending humans to other stars. Perhaps the most radical possibility is that the first true interstellar travelers won't be human in any traditional sense. They might be artificial intelligences seeded with human values and goals. They might be digital uploads of human consciousness running on substrates we haven't invented yet. They might be hybrid beings that combine biological and technological elements in ways that transcend our current categories. The definition of what counts as human is already becoming fluid in ways that would have been unthinkable a generation ago. We enhance our bodies with technology, augment our cognition with external devices, and blur the line between biological and artificial intelligence. By the time we're actually ready to send missions to other stars, the beings making those journeys might be so different from us that calling them human requires expanding that term beyond its current meaning. And maybe that's exactly what needs to happen. Maybe becoming an interstellar species requires us to evolve beyond our current form. Not because space demands it, though it does, but because the very act of reaching toward the stars forces us to transcend our limitations and become something new. Throughout this exploration, we've traced a path from the seemingly impossible to the increasingly plausible. We've seen how technological advances, economic incentives, institutional development, and generational shifts in perspective are all converging to make interstellar exploration not just a dream, but a genuine possibility. But perhaps the most important insight is this. The question of whether we'll ever leave our solar system is really asking whether we're willing to become the kind of beings capable of such extraordinary undertakings. And the answer to that question is being written right now in laboratories, classrooms, boardrooms, and in the minds of people who dare to imagine futures that extend beyond the boundaries of everything we've known. The transformation has already begun. We're already leaving our solar system in the ways that matter most. We're expanding our consciousness, our capabilities, our vision of what's possible. The physical journey to other stars might simply be the final expression of a transformation that's already well underway. We stand at a threshold unlike any in human history. Behind us lies the entire story of our species, confined to one world, looking up at the stars with longing but unable to reach them. Ahead lies a future we can barely imagine, where human presence extends throughout our galaxy, where consciousness spreads across countless worlds, where the story of Earth life becomes a chapter in a much larger cosmic narrative. The choice of which direction we move isn't made by governments or corporations or even by humanity as a whole. It's made by individuals choosing to pursue knowledge, develop technologies, support exploration, and maintain hope that tomorrow can be more extraordinary than today. Every person who looks up at the night sky and feels the pull toward the unknown is participating in the collective decision that will determine our cosmic future. Every student who chooses to study science or engineering, every voter who supports space exploration funding, every entrepreneur who invests in space technology, every dreamer who refuses to accept that the impossible must remain impossible. They're all answering the question of whether we'll ever leave our solar system, and their answer, written in actions rather than words, is becoming increasingly clear. Hyperstudio by Brev.ai input 2,490 words. Output 10,088 words muted. Created at May 18th, 2025 22 53 38. Updated at May 18th, 2025 22 58 31. Model Claude 3.5. Sonnet cost 0.3. 0. Brev Cloud Web App. Try the Hyperstudio web app to run AI workflows, no credit card required. Try it desktop app. Download the desktop app to self-host open source models and run workflows. Download Skip to Main Content Review Article Front. MOL Biosci, 27th November 2024, section. Molecular Diagnostics and Therapeutics. A comprehensive review of proteomic approaches for diagnosing and managing endometriosis. Natalia García Salicia Quijantos, Natalia García Santosuno Goyaso, Alicia Quijano Goyasouno, 2 Emilia Bajilet Lozano, Emilia Bajilet Lozano 1, 2 Cristina López Tintoré, Cristina López Tintoré, 1 Ariadna Gris Martín, Ariadna Gris Martín, 1, 3 Jaume Reventós, Jaume Reventós, 2 Ana Santamaría, Ana Santamaría, 2, 4 Xavier Dolcet, Xavier Dolcet, 1, 2 Estrella, un grup de recerca en biologia celular i molecular del càncer, Departament de Ciència Mèdique Bàsiques, Facultat de Medicina, Universitat de Lleida, Lleida, Spain, 2 Institut de Recerca Biomèdica de Lleida, IRB Lleida, Lleida, Spain, 3 Unitat Ginecologia, Hospital Universitari Arnau de Vilanova de Lleida, Lleida, Spain, Unitat de Ginecologia Oncologica, Hospital Universitar de Bellvitge, Institut d'Investigació Biomèdica de Bellvitge, IDIBEL, l'Hospitalet de Llobregat, Barcelona, Spain. Endometriosis is a gynecological disorder that affects many women worldwide, significantly reducing their quality of life. It is a multifactorial condition that combines hormonal, immunological, genetic, epigenetic, and environmental factors. Currently, diagnosis and management are based on clinical symptoms, physical examination, ultrasound, and invasive diagnostic laparoscopy, followed by histopathological confirmation. However, none of these diagnostic tests have sufficient diagnostic accuracy, often leading to diagnostic and therapeutic delays. Consequently, there is an urgent need for non-invasive, sensitive, and specific diagnostic tools for endometriosis. This review focuses on the potential of proteomics, particularly mass spectrometry-based approaches, as a minimally invasive diagnosis, OSTIC tool for endometriosis. We highlight the utility of high-throughput proteomics to detect multiple biomarkers in biological samples, such as peritoneal fluid, blood, serum, plasma, or endometrial tissue. In addition, we discuss the technical challenges of proteomic approaches and their clinical interpretation to guide patient diagnosis and treatment. Finally, we highlight the future directions of proteomics and artificial intelligence aimed at improving the diagnosis and management of endometriosis. 1 Introduction. Endometriosis is a benign gynecological disease characterized by the growth of endometrial tissue outside the uterus, which may occur on the surface of the ovaries, the pelvic floor, and/or the intestinal mucosa, or in the depth of the myometrium. Sampson, 1927. It affects approximately 1 in 10 women of reproductive age. Boulon et al., 2019. The condition is associated with pelvic pain, dysmenorrhea, dyspareunia, chronic fatigue, and infertility. It is currently estimate diagnostic delay forward that the average endometriosis from the onset of symptoms to diagnosis 8 years, and some is 6 studies have reported delays of 10 years or more. Hudelist et al., 2012. The delay in diagnosis has a significant negative impact on the patient's quality of life. Taylor et al., 2017. For example, it has been reported that 46% of women with endometriosis have moderate or severe pain. Forquet et al., 2010. Whereas 33% of patients are unable to work for an average of 6.3 hours per week due to pain and fatigue. Moradi et al., 2014. This delay can also result in a delay in treatment, which may cause the disease to progress. Therefore, there is a need for an accurate diagnostic method that is fast, inexpensive, and non-invasive to reduce the diagnostic delay. Chaperon et al. Diagnosis of endometriosis is based on L. 2001. The clinical history and physical examination, followed by imaging, transvaginal ultrasound, TVUS, and magnetic resonance imaging, MRI, which is subsequently confirmed by laparoscopy and histopathological analysis of biopsies, Kennedy et al., 2005. Although laparoscopy is the gold standard technique for diagnosing endometriosis, the high invasiveness and variable diagnostic accuracy of the procedure, depending on the surgeon's experience, limit its use as a standard diagnostic tool in some cases. Konings et al., 1991. Moreover, no preoperative tests are available to identify patients suitable for laparoscopic surgery. Consequently, there is a need for a non-invasive diagnostic method that could help clinicians to assess the risk of endometriosis preoperatively and then to assess the risk after surgical treatment. Konings et al., 1991. In this regard, there is a need to identify biomarkers that can be non-invasively detected in various body fluids, such as serum, blood, and urine, in order to develop diagnostic tests for endometriosis. Numerous efforts have been made to find biomarkers, including imaging biomarkers and molecular biomarkers found in various biological fluids and tissues, such as proteins, circulating microRNAs, long non-coding RNAs, metabolites, and even changes in methylation patterns. Proteomics is an ideal approach for this purpose, as it can quantify thousands of proteins from different biological fluids or tissues. This allows for a comprehensive study of the disease and the identification of protein biomarkers that may serve as the basis for novel non-invasive tests. In addition, proteomics can compare element genetic and epigenetic information, providing new insights into the pathophysiology of endometriosis and the underlying signaling mechanisms. By identifying these biomarkers, it is possible to improve diagnosis, classify endometriosis, and identify new therapeutic targets. The aim of this review is to highlight the relevance of the proteomic approach to the study of endometriosis. We will discuss the most recent and promising proteomic studies that aim to identify protein biomarkers suitable for the development of molecular diagnostic tests and/or novel therapeutic targets. 2. Clinical diagnosis of endometriosis. Currently, the diagnosis of endometriosis is based on a combination of clinical history, physical examination, and imaging studies, mainly transvaginal ultrasound, TVUS, and magnetic resonance imaging, MRI, followed by laparoscopic surgery and histopathological analysis of biopsies, Guerriero et al., 2018, Dunselman et al., 2014, Figure 1. However, none of these techniques are fully reliable, which often leads to a delay in diagnosis. Figure 1. www.frontiersin.org Figure 1. Schematic representation of current diagnostic methods for endometriosis. HPE, histopathological examination. MRI, magnetic resonance imaging, TVUS, transvaginal ultrasound, image created with BioRender, https www.biorender.com. 2.1 Medical history and physical examination. Medical history and symptom assessment are the first steps in diagnosing endometriosis. Clinicians inquire about symptoms such as dysmenorrhea, pelvic pain during menstruation, dyspareunia, pain during or after sexual intercourse, chronic pelvic pain, and infertility. They also document the patient's menstrual history, the location and intensity of pain, and any previous treatments or surgeries. This information helps to assess the likelihood of endometriosis and guide further diagnostic testing. Fauconnier and Chaperon, 2005. Physical examination includes a general pelvic examination, a speculum examination, and a bimanual pelvic examination. During the bimanual pelvic examination, the clinician palpates the uterus, ovaries, and surrounding tissues for any signs of tenderness, nodularity, or masses that could indicate endometriosis. A rectovaginal examination may also be performed. This allows the clinician to assess the rectovaginal septum, the posterior vaginal fornix, and the uterosacral ligaments for nodules or tenderness, which are indicative of deep infiltrating endometriosis. Kennedy et al., 2005. A major limitation of the physical examination is its low sensitivity, 47% to 63%. Chaperon et al., 2001, making it difficult to reliably detect the disease. However, physical examination has high specificity, 93% to 100%. Chaperon et al., 2001. Guerriero et al., 2018, which means that positive findings are highly indicative of endometriosis. 2.2 Imaging techniques. After the medical history and physical examination, imaging techniques are used to confirm the diagnosis of endometriosis. Transvaginal nosing, endometriosis. It is recommended ultrasound is the preferred first-line imaging technique for DIAGD by the European Society of Human Reproduction and Embryology, ESHRE. Guidelines for the detection of ovarian endometriomas, OE, and deep infiltrating endometriosis, DIE, as it is cost-effective, non-invasive, and does not involve ionizing radiation. Dunselman et al., 2014. TVUS is highly accurate in diagnosing OE, with a sensitivity of 93% and a specificity of 96%, and is also useful in detecting DIE in the bowel, bladder, uterosacral ligaments, and rectovaginal septum, with sensitivities and specificities ranging from 85% to 98%. Guerriero et al., 2018. Bazot and Darai, 2018. 2018. Transvaginal ultrasonography is also used to characterize uterine abnormalities, such as adenomyosis, which frequently co-occurs with endometriosis. Guerriero et al., 2018. Bazot and Darai, 2018. The main limitation of TVUS is that its accuracy is highly dependent on the experience of the operator. Guerriero et al., 2018. This technique is much less accurate in identifying superficial and peritoneal endometriosis, which is one of the most common forms of endometriosis. Dunselman et al., 2014. In cases where TVUS is inconclusive, or in patients with suspected DIE, MRI is used as a second-line imaging modality. MRI has higher soft tissue contrast resolution than ultrasound, making it excellent for mapping the extent of DIE and identifying adhesions, which are critical for surgical planning. Bazot and Daray, 2018. It is also useful for detecting atypical endometriosis lesions, such as those found in the diaphragm or other extrapelvic sites. MRI has a sensitivity of 94% and a specificity of 77% for the diagnosis of OE, and 94% sensitivity and 77% specificity for the diagnosis of DIE in the rectosigmoid colon. Guerriero et al., 2018. However, compared to TVUS, MRI is more expensive and less accessible. Bazot and Daray, 2018. Although MRI can be useful for detailed mapping of DIE, its sensitivity for detecting peritoneal lesions remains limited, which may result in the disease being underestimated. It has also been reported that MRI is not useful for the diagnosis of superficial endometriosis. Medeiros et Leighton, 2015. 2.3 Laparoscopy and histopathological analysis. Despite advances in imaging techniques, diagnostic laparoscopy is still the gold standard for the definitive diagnosis of endometriosis. Kennedy et al. 2005. This minimally invasive surgical procedure allows direct visualization of the pelvic cavity and the identification of endometrial implants. Suspected lesions can be biopsied during laparoscopy for histopathological examination and to confirm the presence of endometrial glands and stroma outside the uterus. Histopathological examination of the biopsy is necessary to confirm the diagnosis and to rule out other conditions, such as malignant neoplasms. Direct visualization during laparoscopy allows the surgeon to assess the extent and severity of the disease and classify it according to one of several classification systems. However, there is no universal agreement on the most appropriate classification system. The most commonly used and recognized classification systems are the American Society of Reproductive Medicine, ASRM, Canis et al., 1997, and the Enzian classification systems, Keckstein et al., 2021, which are based on laparoscopic findings or histopathological analysis and provide a stage of the disease that is useful for planning treatment. However, laparoscopy has several limitations. First, the accuracy of the procedure depends on the surgeon's expertise in identifying subtle or atypical endometriotic lesions. In addition, laparoscopy may not detect microscopic or deeply embedded lesions, which can lead to an underestimation of the extent of the disease. Kennedy et al., 2005. The invasive nature of the procedure also carries risks, including complications such as infection, bleeding, and damage to surrounding organs. These risks, along with the costs associated with surgery and the need for general anesthesia, make laparoscopy less than ideal as a routine diagnostic tool, especially for patients with mild or suspected disease. Gupta et al., 2008, Nissenblatt et al., 2016 IE. Moreover, there is no reliable preoperative diagnostic test to determine which patients are most likely to benefit from laparoscopy. This lack of a reliable non-invasive diagnostic test leads to unnecessary laparoscopies in some patients and delayed diagnosis in others. The current guidelines from the ESHRE, Dunselman et al. 2014, and the National Institute for Health and Care Excellence, NICE, Idiriman et al. 2021 do not require histopathological confirmation for the diagnosis of endometriosis unless imaging findings are inconclusive or surgical intervention is planned. This decision is based on the consideration that, although histopathological examination is the gold standard for confirming the presence of endometrial tissue outside the uterus, it is not always feasible or necessary in all cases. For example, if imaging techniques such as TVUS or MRI provide clear evidence of endometrioma or deep infiltrating endometriosis, DIE, and the patient's clinical presentation is consistent with endometriosis, treatment may be initiated without histology. CAL confirmation. This approach aims to reduce the need for invasive procedures while ensuring that patients receive timely treatment. Dunselman et al. 2014, Idiriman et al. 2021. However, the decision to forego histopathological confirmation should be made on a case-by-case basis, considering factors such as the patient's age, the severity of symptoms, the presence of risk factors for malignancy, and the patient's preference. In cases where the diagnosis is uncertain, or when malignancy cannot be excluded based on imaging findings alone, histopathological examination remains essential. Dunselman et al. 2014. 2.4 Limitations of current diagnostic approaches and the need for biomarkers. Despite the availability of these diagnostic methods, none provide sufficient accuracy for the early and reliable detection of endometriosis. The main limitations include imaging techniques. TVUS and MRI are excellent for detecting ovarian endometriomas and deep infiltrating endometriosis, but have limited sensitivity for superficial peritoneal lesions, which are the most common form of endometriosis. Laparoscopy, while considered the gold standard, is invasive, expensive, and carries surgical risks. Its accuracy depends on the surgeon's experience, and it may miss microscopic or deeply embedded lesions. Physical examination has low sensitivity and may not detect early-stage disease. There is no reliable non-invasive preoperative test to identify patients who would benefit most from laparoscopy, leading to unnecessary surgeries in some cases and delayed diagnosis in others. These limitations highlight the urgent need for non-invasive, accurate, and cost-effective biomarkers for the diagnosis of endometriosis. Biomarkers could enable early detection, reduce diagnostic delays, minimize the need for invasive procedures, and improve treatment outcomes. In recent years, various molecular approaches have been explored to identify such biomarkers, including proteomics, genomics, metabolomics, and transcriptomics. Among these, proteomics has emerged as a particularly promising approach due to its ability to identify and quantify proteins that may serve as diagnostic, prognostic, or therapeutic targets. 3 proteomic approaches in endometriosis research. Proteomics is the large-scale study of proteins, including their structures, functions, interactions, and modifications. Unlike genomics, which provides information about potential gene expression, proteomics offers direct insights into the functional molecules that drive cellular processes. In the context of endometriosis, proteomic studies aim to identify protein biomarkers that can improve diagnosis, classify disease subtypes, predict disease progression, and identify potential therapeutic targets. 3.1 Rationale for using proteomics in endometriosis. Endometriosis is a complex, multifactorial disease involving hormonal, immunological, genetic, and environmental factors. The disease manifests with significant heterogeneity in terms of clinical presentation, lesion location, and response to treatment. This complexity makes it challenging to develop a single diagnostic test based on a single biomarker. Proteomics offers several advantages in this context. High throughput analysis. Proteomic technologies can simultaneously analyze thousands of proteins in a single sample, providing a comprehensive molecular profile of the disease. Identification of novel biomarkers. Proteomics can identify proteins that are differentially expressed in patients with endometriosis compared to healthy controls or patients with other gynecological conditions. Insights into disease mechanisms. By identifying dysregulated proteins and pathways, proteomics can provide insights into the underlying mechanisms of endometriosis, potentially revealing new therapeutic targets. Non-invasive sampling. Proteomic analysis can be performed on minimally invasive or non-invasive samples, such as blood, serum, plasma, urine, or menstrual fluid, making it suitable for routine clinical use. 3.2 Sample types used in endometriosis proteomics. Various biological samples have been used in proteomic studies of endometriosis, each with its own advantages and limitations. 3.2.1 Peritoneal fluid. Peritoneal fluid, PF, is the fluid that surrounds the pelvic organs and is in direct contact with endometriotic lesions. It contains proteins, cytokines, growth factors, and immune cells that reflect the local microenvironment of the disease. Several studies have analyzed the proteome of PF to identify biomarkers associated with endometriosis. Ferrero et al., 2009. Wolfler et al., 2013. Ahn et al., 2010. However, the collection of PF requires laparoscopic surgery, making it invasive and not suitable for routine diagnostic use. Nevertheless, PF analysis has provided valuable insights into the pathophysiology of endometriosis and has helped identify candidate biomarkers that can be further validated in less invasive samples. 3.2.2 Blood, serum, and plasma. Blood-based samples, serum and plasma, are among the most commonly used specimens in biomarker research due to their accessibility and minimally invasive collection. Several proteomic studies have analyzed serum or plasma from patients with endometriosis to identify diagnostic biomarkers. Gupta et al., 2006, Hirsch et al., 2004, Mihaly et al., 2010. However, blood proteomics faces several challenges, including the high dynamic range of protein concentrations, spanning over 10 orders of magnitude, the presence of highly abundant proteins, such as albumin and immunoglobulins, that can mask less abundant proteins, and the variability introduced by sample collection and processing. 3.2.3 Endometrial tissue. Endometrial tissue from women with endometriosis often shows molecular differences compared to tissue from healthy women. Proteomic analysis of eutopic endometrium, endometrial tissue within the uterus, and ectopic endometrium, endometrial tissue outside the uterus, can provide insights into the molecular mechanisms underlying endometriosis. Kiyama et al., 2011, Zhang et al., 2016. However, tissue collection requires invasive procedures, and the use of endometrial tissue as a diagnostic sample is limited by its invasiveness. 3.2.4 Urine and menstrual fluid. Urine and menstrual fluid are completely non-invasive samples that can be easily collected. Some studies have explored the use of these samples for proteomic analysis in endometriosis, Chen et al., 2016. However, these sample types present challenges such as low protein concentrations, high variability, and contamination with cellular debris. Despite these challenges, they remain attractive options for non-invasive biomarker discovery. 3.3 Proteomic technologies. Several proteomic technologies have been applied to endometriosis research. The most commonly used approaches include 3.3.1 Two-dimensional gel electrophoresis, 2DE. Two-dimensional gel electrophoresis was one of the earliest proteomic techniques used to separate and identify proteins based on their isoelectric point and molecular weight. This method was widely used in early endometriosis studies to identify differentially expressed proteins. Ferrero et al., 2009. However, 2DE has several limitations, including low sensitivity, limited dynamic range, difficulty in detecting low abundance proteins, and challenges in reproducibility. 3.3.2 Mass spectrometry, MS. Mass spectrometry has become the gold standard for proteomic analysis due to its high sensitivity, specificity, and to identify and quantify thousands of proteins in a single experiment. Several MS-based approaches have been used in endometriosis research. Surface-enhanced laser desorption / ionization time-of-flight mass spectrometry, SELDI-TOF-MS. This technique was used in some early studies to identify protein profiles in serum or plasma that could distinguish women with endometriosis from healthy controls. Gupta et al. 2006, Hirsch et al. 2004. However, SELDI-TOF-MS has limitations in terms of reproducibility and the identification of specific proteins. Liquid chromatography tandem mass spectrometry, LC-MS/MS. This is currently the most widely used proteomic technique. It involves separating proteins or peptides by liquid chromatography and then analyzing them by tandem mass spectrometry. LC-MS/MS allows for the identification and quantification of thousands of proteins with high sensitivity and specificity. It has been widely used in endometriosis research to identify protein biomarkers in various biological samples. Mihaly et al. 2010, Kiyama et al. 2011, Zhang et al. 2016. Targeted proteomics, selected reaction monitoring / multiple reaction monitoring, SRM/MRM. This approach focuses on the quantification of specific proteins of interest with high sensitivity and reproducibility. It is often used for validating candidate biomarkers identified through discovery proteomics. Rifai et al. 2006. 3.3.3 Protein microarrays. Protein microarrays allow for the simultaneous measurement of multiple proteins in a single sample using antibodies or other capture agents. This technology has been used in some endometriosis studies to measure cytokines, growth factors, and other proteins in serum or peritoneal fluid. Vodolazskaya et al. 2012. However, Protein microarrays are limited by the availability and specificity of antibodies. 3.4 Key findings from proteomic studies of endometriosis. Numerous proteomic studies have been conducted over the past 2 decades to identify protein biomarkers for endometriosis. These studies have analyzed various sample types and have identified hundreds of proteins that are differentially expressed in women with endometriosis compared to controls. Some of the key findings include 3.4.1 CA125, cancer antigen 125. CA125 is the most widely studied biomarker for endometriosis. It is a glycoprotein that is elevated in the serum of some women with endometriosis, particularly those with advanced disease. However, CA125 has limited sensitivity, 28% to 52%, and specificity, 78% to 93%, for diagnosing endometriosis, particularly in early-stage disease. Moll et al., 1998. Elevated CA125 levels are also observed in other conditions, such as ovarian cancer, pelvic inflammatory disease, and uterine fibroids, which limits its diagnostic utility. As a result, CA125 alone is not sufficient for the diagnosis of endometriosis, but it may be useful when combined with other biomarkers or clinical findings. 3.4.2 Inflammatory and immune-related proteins. Endometriosis is associated with chronic inflammation, and numerous studies have identified elevated levels of inflammatory cytokines, chemokines, and immune-related proteins in peritoneal fluid, serum, or endometrial tissue of women with endometriosis. These include interleukins, IL-6, IL-8, IL-1 beta. These pro-inflammatory cytokines have been found to be elevated in peritoneal fluid and serum of women with endometriosis and are thought to contribute to the inflammatory microenvironment that supports the growth and survival of endometriotic lesions. Bedawi et al. 2002. Tumor necrosis, factor alpha, TNF-alpha. TNF-alpha is another pro-inflammatory cytokine that has been found to be elevated in women with endometriosis and may play a role in disease pathogenesis. Bedawi et al. 2002. C-reactive protein, CRP. Some studies have reported elevated levels of CRP in women with endometriosis, although the findings have been inconsistent. Vodolazskaya et al. 2012. 3.4.3 Angiogenesis-related proteins. Angiogenesis, the formation of the new blood vessels, is essential for the establishment and growth of endometriotic lesions. Several angiogenesis-related proteins have been identified as potential biomarkers. Vascular endothelial growth factor, VEGF. VEGF is a key regulator of angiogenesis and has been found to be elevated in peritoneal fluid and serum of women with endometriosis. Metaliotakis et al. 2008. Angiopoietin-1 and angiopoietin-2. These proteins regulate blood vessel formation and have been found to be differentially expressed in endometriosis. Tan et al. 2002. 3.4.4 Adhesion molecules. Cell. Adhesion molecules play a role in the attachment of endometrial cells to ectopic sites. Some studies have identified altered expression of adhesion molecules such as intercellular adhesion molecule 1, ICAM1. Elevated levels of ICAM1 have been reported in peritoneal fluid of women with endometriosis. Daniel et al. 2007. E-cadherin. Altered expression of E-cadherin, a key cell adhesion molecule. has been observed in ectopic endometrial tissue, Matsuzaki et al., 2010. 3. Tonight, as you've journeyed with us through the complex landscape of endometriosis diagnosis and the revolutionary potential of proteomics, we've uncovered something profound. This isn't just about developing better tests or finding new biomarkers. It's about transforming the lives of millions of women who have spent years searching for answers to their pain. The convergence of mass spectrometry, artificial intelligence, and our growing understanding of protein signatures in biological samples is creating possibilities that seemed impossible just a decade ago. We're moving toward a future where diagnosis won't require invasive surgery, where treatment can be personalized based on molecular profiles, where the 8-year diagnostic delay becomes a relic of the past. The proteins circulating in blood, present in peritoneal fluid, or expressed in endometrial tissue, are telling us stories about disease mechanisms we're only beginning to understand. Each proteomic study adds another piece to this intricate puzzle, bringing us closer to the comprehensive diagnostic tools that clinicians desperately need and patients rightfully deserve. But perhaps most importantly, this research is revealing that endometriosis isn't just one disease with one signature. It's a spectrum of conditions with distinct molecular profiles, different inflammatory patterns, and varied responses to treatment. Understanding this complexity through proteomic analysis is opening doors to targeted therapies that address the specific mechanisms driving disease in individual patients. The journey from discovery to clinical application remains challenging. Technical hurdles, validation requirements, and the need for standardization across studies remind us that transforming research findings into routine diagnostic tests demands patience, rigor, and collaboration across disciplines. Yet the momentum is undeniable. Every advance in proteomic technology, every new biomarker validated, every machine learning algorithm refined, brings us closer to revolutionizing how we diagnose and treat endometriosis. Thank you for exploring this frontier of medical science with us. Until next time, stay curious, keep wondering, and remember that behind every protein signature we discover lies the potential to change someone's life. This is the future of endometriosis diagnosis, and it's arriving faster than we ever imagined. Endometriosis diagnosis, and it's arriving faster than we ever imagined.